Hello everyone, today I'm going to show you how we can find a closed formula for the Fibonacci sequence. The Fibonacci sequence is a pattern of numbers where the next number in the sequence is the sum of the two previous numbers. So in math, that would look like this, where the nth number is the sum of the previous two numbers. So f of 0, or the 0th number, is 1, and f of 1 is also 1. And if we list the numbers out, we start with 1, 1, and the next number is going to be the sum of the two previous numbers. So this becomes 2, 2 plus 1 is 3, 3 plus 2 is 5, 5 plus 3 is 8, 8 plus 5 is 13, and so on. But let's say we wanted to find like the millionth number. Well, there's no way to do that quickly without calculating all of the previous numbers before that. Because to find that number, we would need to know the one right before it and the one before that one. And so today, we're going to find a way that we can just plug in an n and we can get back the number that would be in the sequence at that place. So first, we can start off by recognizing a pattern. So we know f of 2, or this 2, is equal to f of 1 plus f of 0, the two previous numbers. Also, f of 1 is just f of 1. But we can kind of represent this as a vector if we do plus 0 times f of 0, because 0 times anything is 0. And so f of 1 will always equal f of 1. This will always be true. And if we represent it as a vector and matrices, we can set it like this. So f of 2 is equal to this matrix, or a vector. And we can take out the coefficients so that it's 1, 1, 1, 0 times the vector f of 1 and f of 0. Because if we multiply, or if we do the matrix multiplication here and here, we get back what's over here. Now what about the next numbers? So like f of 3 and f of 2. Well, f of 3 is f of 2 plus f of 1. And we're going to do the same trick kind of here, where f of 2 is 1 f of 2 plus 0 f of 1s. And then we can do the same process, take out the coefficients, and we multiply it times the vector f of 2, f of 1. And now we already know what this vector is equal to. It's f of 2 and f of 1 is equivalent to this, so we can substitute it into that. We find that f of 3, f of 2, this vector, is equal to this. And since these matrices appear twice, we can write it as it squared times f of 1 and f of 0. So I hope you're starting to see the pattern here. And now I'm going to do it in general. So in general, f of n and f of n minus 1 is going to be equal to this matrix here to the power n minus 1, because here these have to match, times f of 1 and f of 0. So now using matrix diagonalization, which says that if we have a matrix D, we can represent it as a multiplication between three other matrices. The inverse matrix of its eigenvectors, then a diagonal matrix of its eigenvalues, and then the matrix whose columns are the eigenvectors of D. And this is useful because since A is a diagonal matrix, which means that it has entries only along its diagonal and everything else is 0, it means finding it, like when we raise it to a power of k, is simply multiplying these. Since everything else is 0, we don't have to perform big computations. So that's why this is useful. We can write d to the power of k. We can find it easily by multiplying a k times. So now let's find these matrices for this one right here. So to find the eigenvalues, the determinant of 1 minus lambda, 1, 1, and 0 minus lambda is negative lambda. We set that equal to 0. Then we take the determinant of a 2 by 2 matrix by finding the product of these two entries and subtracting the product of these two entries. So we take the product of these two and we subtract 1 times 1 is 1. We set that equal to 0. And if we distribute the negative lambda, we get negative lambda plus lambda squared minus 1 equal to 0. And we need to find the values of lambda that satisfy this. So this is just a quadratic, and we can find the values of lambda using the quadratic formula. And so from the quadratic formula, our a is equal to 1, the coefficient, b is equal to negative 1, and c is also equal to negative 1. So if we use the quadratic formula, we know lambda is equal to negative 1 is positive 1, plus or minus the square root of b squared minus 4 times a times c divided by 2 times a. And let's simplify what's inside the radical. So we have negative 1 squared is just 1. And then negative 4 times 1 is negative 4 times negative 1 is plus 4 divided by 2. And this becomes 1 plus or minus the square root of 5 over 2. So these are the two eigenvalues. Then we would find the eigenvectors and the inverse of that matrix. But since it's just a 2 by 2, I'm just going to use a calculator. Okay, so now we have the matrix decomposed into the 3 different ones, where this is the eigenvalues, the eigenvectors, and the inverse of the eigenvectors. If we raise it to the kth power, we only have to raise the middle matrix, the eigenvalue matrix, to the power of k. Okay, but in this case, we want it to be raised to the power n minus 1. This matrix raised to the n minus 1 power, we can just raise all of the entries to the n minus 1. So if we multiply these, they actually have the same base, and what that means is we add the exponents. So this has an exponent of 1, and if we add 1 plus n minus 1, the 1's cancel out, so we just get this entry raised to the n. And the same thing here, if we multiply these and here, these have the same base, so again it's going to be raised to the power of n. Now if we do the second row times the first column, we get 1 times this entry plus 0 times 1, and 1, we just get back this entry. Same thing if we multiply the second row times the second column. And remember that all of this is still equal to this raised to the n minus 1. And now we can do the substitution. So if we put this into here, we get the following. Okay, so we're getting a lot closer to the closed formula. So we know the entry f of n is equal to this row times this column. And then from here, we can factor out a negative square root of 5 over 5. Alright, so after all of this arithmetic, we find that the closed formula for f of n is equal to this guy right here. And so now if we wanted to find, let's say, like the 30th number, we could simply put in 30 for n, do the algebra, and we would get back the number 832,040. So this tells us, if you remember from the beginning, that the 30th number in the sequence is 832,040. Alright, so that's going to be the end of this video. I hope you enjoyed. If you have questions, leave them in the comments, and thank you for watching.